let's go ahead and get started. Again, my name is Laura Beth, and I'm your host. So I'll be keeping an eye on the chat for questions. And I'm so happy to have Doug Lively here, our special guest. And Doug is a ambassador, sorry, a solar system ambassador from NASA and JPL. Word just escaped me. So hello, Doug. Everyone say hi to Doug.
Hey, everybody.
Hey, thanks so much for joining us.
Thank you all for coming today. We're going to have a fun talk today, so this will be a fun one to have.
I'm excited.
All right, so let's go ahead and get again. My talk is on deadly seers, the top 10 ways the solar system can kill, maim, or really hurt you. And so this is really a talk about the solar system and solar system objects. Now, these are 10 ways that things can and do go wrong in our solar system. They're not the only things that can and do go wrong in our solar system or in the cosmos. So definitely we can talk about some of those things after the end of the discussion on the topic. So, but anyway, before we actually get into the talk, I do want to just kind of give out a shout out to Raleigh Astronomy Club. I'm also a member of the Raleigh Astronomy Club. I'm a former co-chair. I've been with the club for about 22 years or so. And to just let you know, when I started with the club, I was a complete novice. I couldn't even point to the North Star in the sky. I just really didn't know a lot. I just knew that inside I had a passion for the night sky, that there was something about it that really attracted me. I didn't even own a telescope. And so I just joined the club just to, find out more. And they really helped me in terms of nurturing my passion for the night sky and actually growing in my knowledge. So to you, the listeners out there, if you think that you just have this passion for the night sky and you really want to learn more about it, the Raleigh Astronomy Club is for you. We actually meet in Raleigh. We're at the, when we're not on social distancing and under a pandemic, we meet at the NCSU Craft Center on 210 Jensen Drive, usually second Fridays of the month. And it's open to the public. You're welcome to come. You don't even have to join the club to come. We're really there to invite the public. But again, if you have a passion or something like that, we do a lot of public outreach. All of our events, meetings and stuff are open to the public and they're free. So we would love to just invite you to come and just check it out. Currently, though, due to social distancing, due to our own restrictions here in North Carolina now, all of our meetings and events are virtual, including observing sessions. So if you have a chance to join one of our virtual observing sessions, it's a real treat. We do all of us are actually doing our observing from our driveways with specialized astronomy cameras on our telescopes. So you actually get to see events real time as they're coming through the scope. So just want to give that shout out to Raleigh Astronomy Club. And so now let's get on into deadly spheres. Again, this talk is really going to be a fun talk about our solar system and to just kind of let you know about some of the structures and some of the things that do go wrong in the solar system. So the first thing I want to point out is this was your granddaddy's solar system. So our knowledge of the solar system has really increased over the last 50 years. And the reason why I can tell you that this is your granddaddy's solar system, because I'm a granddaddy. Actually, I'm a great-grandfather. And this was the exact map I had hanging on my wall when I was about 10 years old. And this is a fairly famous one. It's funny how our knowledge has grown over the years. At that time, there were 9 planets, and we hadn't visited a single one. We hadn't even visited the moon yet. And so we didn't have pictures from the moon. We didn't have pictures from Mars. There were no pictures from Venus, Mercury, or any of the other planets. We really didn't know what they looked like. And so this map was just a speculation of what the planets might look like. If you look up here in the upper right-hand corner, there's even a picture of the asteroid Ceres.
And sorry, real quick, can you share your screen so that we can see the map?
Thank you.
I did the same thing. It's very clear that this is the first Astronomy Days program of the day, right?
Yeah, exactly. There we go. Can everybody see that map?
Yes. Yeah.
Perfect. Great. Thank you. Okay. So again, we didn't know what an asteroid even looked like. So if you look here to the upper right-hand corner, this is the asteroid Cirrus. They thought that Cirrus looked like this. And well, now we know. We've actually visited Cirrus with a probe, and we know that it's really a minor planet, and it's round, not unlike our moon. So it's so things have changed over the years. So our perception of the solar system has changed with knowledge. Now, this is what our solar system looks like today. Before we go to our solar system, let me just say one thing is that it's also not your granddaddy's galaxy anymore either, because our perception of the galaxy has really changed over time. Now, this is not an actual picture of our galaxy. It's just a simulation. But the idea is that we live in a spiral bar galaxy. That's that bar right here. You see, it's not an actual bar. It's just that the ellipsis in the galaxy is elongated like a bar. And then we are actually, and I'm just going to click the next slide. Here's where our sun is. It's right there, kind of off center from the galaxy. We're not at the center, and it's a good thing we're not, because at the center of our galaxy, there's a supermassive black hole. There's a lot of radiation, things blow up a lot, not a good place for life. But where our sun is situated about 2/3 of the way out of the galaxy, and it's in between these really cool arms, the Sagittarius arm and the Orion spur. And so it's a really nice place for life to be, and so it's very quiet for us. It's kind of boring with respect to the rest of the galaxy, where you see all these red dots and coloration is where, again, things are exploding or new suns and stuff are being born. And so again, not a good place for life. So many of the new programs with NASA and research programs for looking at stars in the sky are looking actually in these quiescent pieces of the galaxy now, whereas before we were just looking all over. We really didn't understand a lot about how our own planet came into existence. So now, with greater understanding, we're now looking in these quiet arms. So anyway, we're going to be looking right around here at our sun and what's happening in that solar system. And this is what our solar system looks like today. Again, this is not your granddaddy's solar system. We're seeing the sun, this lower panel here, moving through our galaxy, and the planets are actually spiraling around it. If you look here in this upper panel, you can see that our sun is kind of traveling along the edge of our galaxy, and the planets sometimes lead, sometimes they trail, and there again, it's kind of more this spiral effect. If you look here in the lower left, we're now looking kind of at the outer structure of our solar system with this thing what we call the heliosphere. We didn't even know this until after the Voyager 1 and Voyager 2 spacecraft got near the edge of our solar system to actually be able to see more or less what this structure looks like. Out here on the right is interstellar space, but in here is actually our solar system. And you can see that the heliosphere from our sun, this is where our sun's influence actually protects our solar system from outcoming or incoming cosmic radiation. You can see that it's really stretched way out into space. So this is more or less the structure of the solar system. We are going to learn more as the years go by and as more probes go out about really what this structure looks like. We're still really in the infancy stage of learning about what our actual structure is. Some of the other things that we've been able to also solidify was at one time theorized, but now we're fairly confident in the structure of, there's an outward disk out here in the outer solar system called the Kuiper belt. And so we have the short periodic comets generally come from what we call the Kuiper belt. It's this disk right here that you see me circling with this red cursor. Down below on the outer shell of our solar system is a cloud known as the Oort cloud, which we think contains billions of comets and long periodic comets. When I say a periodic comet, it means one that comes around periodically. So short ones are like in tens of years, like Halley's Comet and so forth. And others are in thousands of years, like Comet Neowise, which has like a 65,000 year orbit. So out in these bodies, we really are just beginning to learn what's out here. And so there could be some scary things out there, things that we haven't discovered. One of the things that we think might be happening in the outer edges of our solar system is a primordial black hole. So let me just explain that for a moment. You know, if you listen to many of the science programs of over the past few years, they're like, oh no, black holes are just, you know, millions of light years away. We don't really have anything to worry about. So we should be fine, but maybe not so much. So let me just give a little history on this. A number of years ago, actually only 7 years ago now, there was a team of scientists looking at the outer edges of our solar system. And they noticed that some of the bodies, the bodies that they were looking at seemed to be perturbed, moved around by a massive object. And they didn't know what it was. And so they assumed that this object might be a ninth planet. And so we called it Planet 9, and we began looking for it. And so given the way that those objects were moving around, how they were pushed around, they thought that there might be a planet out there roughly about 200 times, or 200 AU, from the sun. If you know what an AU, that's an astronomical unit, that's the distance from Earth to the sun. And that distance is 93 million miles. So you multiply 93 million miles times 200, that's how they said 200 AU. That's how far they believe this planet is away from the sun. Now it has an orbit on the orders of thousands of years, but they began looking for it. Well, again, they thought it might be about 5 times the size of Earth. That should be, you know, relatively easy to spot, especially if you see where everything's moving around in the outer solar system. You should be able to find this thing. Well, after 7 years of actually searching, they've found nothing. They can't find anything. So now the idea has recently shifted to the point that there might be a primordial black hole at the edge of our solar system. And I'll talk about what a primordial black hole is versus a regular black hole. So in this next slide, at the center of our galaxy, there is a supermassive black hole, something that's got roughly on the order of 20,000 solar masses at that. And right now I'm looking at our galaxy's black hole. This is the 2 panels, this far left panel, and then when you see these stars moving around, this is sort of like what they saw near the edge of our solar system. They could see that planets and small objects and stuff like asteroids and small planetesimals were being moved around by some mass. They couldn't see it. Now, on this left here, this is the constellation Sagittarius. It sort of looks like a teapot, and this is mostly kind of a summertime object. And if you look right here, this is the spout of the teapot right here. And right in this area is actually the center of our galaxy. So in the summer, when it gets to be summer and you go out on a nice summer's evening, you're looking at the Milky Way, you're looking at Sagittarius, just note that just off the tip of this T-spout here is actually the center of our galaxy, and that's where we have our galaxy's supermassive black hole. Again, it's got about 20,000 times, 20,000 times the mass of our sun. So it's a supermassive black hole. It actually holds our galaxy together, and its gravitational pull is what actually holds our galaxy in place. So everything else would be flying off. So it's got a very powerful gravitational attraction. Fortunately, again, we're far enough out that we're not, and we're in a very stable orbit, we're not in any danger of falling into that black hole. On the right here, far right, you might have recognized this picture. This is the actual first image of a black hole. It was taken a couple of years ago by a team of scientists working from different places all over the world. And they were actually able to image this black hole. It's an M87, which is a Messier object. It's a galaxy, another galaxy. It's about 53 million light years away. And it's if you go to look at it, it's in the constellation Vulpecca. M87 is a common object that many amateur astronomers look for in the Messier list. So you can always find that object. Now, you won't be able to see this black hole even in the most powerful telescopes. This image actually came to us from the world's most powerful radio telescopes. So this is actually a radio image and not a visual image of that black hole. Now, a primordial black hole, let me go back just a second before we go to this. A primordial black hole is very different from a massive black hole. Primordial black holes are much, much smaller. These are believed to be black holes formed not long after the beginning of the universe. And over time, they have shrunk. Now, the black holes can shrink. This is what Stephen Hawking discovered, what we call it now, Hawking radiation. And we realized that black holes are not perfect. They actually do starve. And over time, as they starve, this kind of flow of radiation called Hawking radiation actually causes them to leach, and they get smaller and smaller and smaller. So that's what a primordial black hole is. If it never got fed and it just basically over time starved, it became smaller and smaller and shrunk. And so this is a supermassive, these are supermassive black holes. We think we have a primordial black hole at the edge of our solar system. Okay, so if a
real quick, before you move on, sorry, we had a couple people asking why in that picture it looks reddish orange.
Yeah, okay, so that's a good question. That would be the wavelength of light that's coming back in the electromagnetic spectrum that's coming back from the radio to the radio telescope. And so you're getting those reds and oranges. Plus two, it's also very hot around the black hole, because you got to think about what happens around the black hole. You reach a point where objects can no longer stay connected. So in this picture here, you can see that you've got the Earth and a supermassive black hole opening up around it. Excuse me just one second, my cursor's gone away, there we go. This massive black hole is opened up around it, and the Earth is beginning to be split apart. And so you reach a point where objects become stretched and they begin losing their shape. And of course, there's a lot of heat and energy that's being released. In the case of a radio telescope image, it's going to be in the red spectrum because there's a lot of heat and energy as a result of that dissolving matter. And so that matter actually becomes stretched, distended, and dissolved as it gets closer and closer to the black hole. And that's what we're seeing there. It's kind of in that, what we call the Roche limit. It's a limit where gravity from one object on one side of the object is pulling it away from the other side, and it's being stretched, pulled, and a lot of energy is being released at that point. So not sure if that answers the question, but I hope it does.
Yeah,
Thanks.
That's super interesting. And Joe says, let's not let that happen.
Yes, let's hope not. So here, this is what would look like if the Earth actually, got in front of a supermassive black hole. We would literally suck basically all of our atmosphere and then our water away, and then it would begin, chunky pulling away at our Earth and breaking it apart. So that's, again, a supermassive black hole would do that, and it would only be a matter of seconds, and we'd probably be consumed. So it'd go quickly, that's for sure. But we're not in that situation. The closest one is probably about 1,000 light years away, so we're in pretty good shape. And then the supermassive black hole at the center of our solar system is roughly about 50,000 light years away, so we're in pretty good shape that we're not going to be eaten by a supermassive black hole. But back to our subject, which is the other black hole, which is the primordial one. It's got the size between 5 and 15 Earths, but it's only about the size of maybe a grapefruit or a really large basketball. And I will say that it's in a very stable orbit, so we're not in any danger of that actually hitting the Earth. Now, I've read a couple of papers on this. A lot of people are conflicted about what would happen to the Earth if it actually hit. So I will tell you that the jury is still out on this one, but the feeling is that it would really just pass through the Earth. It actually wouldn't rip the Earth apart, but it would probably pass through the Earth, creating, at that point, creating a lot of explosion as it passed through the Earth, but it wouldn't actually tear the Earth apart. So that's kind of the theory, but no one really knows. So, but again, this in a very stable orbit on the order of, I believe it's 56,000 years to make an actual orbit. So we're in pretty good shape. Yes, and I do see that question. Black holes do move. They do move through space. Yes. All right. All right. So we'll move on. If there are any more questions, then I'll move on to the next one. This one we don't really have to worry about. The conclusion is you really don't have to worry about a black hole, hitting the Earth anytime soon.
I don't see any questions, but
all right. Well,
yeah.
All right. So somebody at the very beginning asked about comets, and yes, that is something we need to worry about. So let me just these are three famous comets that have been around. These have all been visual comets. This is Hakataki on the right. We have Hakataki, which is the one that was really beautiful right there in the late 90s. This was a very classic, beautiful comet you could see in the night sky. This one is on the left here is Comet Lovejoy with this beautiful green coma here. This was actually came around about 4 or 5 years ago. A really beautiful comet, and it was a visual one that you could see in the night sky. But most recently, if you look down here in the lower right, we have Comet Neowise. And hopefully some of you guys have had a chance to go out and see this. This is an actual photo that Mike Keefe, one of our astronomers at Raleigh Astronomy Club and a fellow NASA SSA, took of Comet Neowise. And I got a lot of pictures of it myself. It was an early morning, and then it was an early evening object back in the June-July timeframe. So just to tell you a little bit about comets. Comets all have three main components. They have a core, which is basically, or nuclei, which is composed of ice and dust, small rocky materials, silica. They have like some of them have some really dangerous chemicals like cyanide in them, ammonia and methane, or they could have oxygen and carbon dioxide. Other heavy metals like platinum have been detected in these things. So the core nuclei of the comet are just kind of like building blocks that were left over after the formation of our solar system. So they're really neat to look at. They're fabulous. But anyway, this is the core nuclei. The coma of the comet is usually kind of this fuzzy envelope that kind of forms around the comet. As it's coming towards the sun is sending out solar wind, and it's hitting the comet, causing it to kind of fluoresce, and it's also causing this breaking apart some of those chemicals that are bound in the silica, and it's kind of raising up like a fog around it. And so that becomes this kind of nebulous coma. And then the comet has a tail. So as it approaches the sun, the solar wind is running out about sometimes between 350 to 600 kilometers per second. So it's pretty fast, and it's hitting the comet, blowing material off the end of the comet. So when it gets closer to the sun, the tail usually becomes longer and brighter. So let me just kind of go back to our previous slide, and you can see, if you look here on Comet Lovejoy, right here on the left, you can see that there's the very white piece, that's the nucleus. This green area is the coma, and that's where we actually see this, like again, that fog that I was looking at, telling you about. If you were to look at a comet when it's way out in the solar system, it looks kind of like a fuzzy snowball coming towards you. That's a lot of people describe it as that. And then we have this tail coming out here, this tail portion. Now, Comet Hakataki was basically different because it actually has two tails. You see this tail, you have the regular material that's being blown off, but then we have this really bright blue tail coming off here. And this is known as an ion tail. And this is a tail of electrically charged particles that are actually coming off. Not all comets show, display an ion tail. So it's very neat to be able to see one of these. And we've have had a few come around, but nothing as bright or as beautiful as this particular comet was in the late 90s. So just to let you know, that's sort of the structure of a comet. Now, comets can be relatively small, tens of kilometers, or they could be relatively large. Now, there was a recent orbiter around a comet. This is the comet CHURYUMOV-GERASIMENKO, excuse me for the pronunciation. But this was actually, we sent a probe around this, and we actually landed the little Philae lander on this comet a few years ago. Now this comes from the ESA. They basically took that comet and superimposed it on LA. And you can see with relief, this would be the size of the comet with respect to the city LA. So it's huge, right? It's only a few kilometers in diameter, but it's massive. Now, the first thing it should tell you is that if we're going to take care of comets, you can't nuke that thing, okay? A nuclear device just isn't going to take care of something that massive. It might take care of LA, but you're not going to take care of that entire comet. The other thing too is you don't really want to nuke a comet. Let's say you were able to successfully blow up a comet before it hit the Earth with a nuclear device. Well, what would happen is then it would just break up into smaller radioactive chunks and rain down on Earth. So using a nuke to try and divert a comet is not really a good idea. So now the question is, though, do comets make impact? Do they pose a danger to Earth? And there is a danger. So let me just, some of you may not be old enough to remember this, but back in 1994, there was, actually 93, there was a comet that came around called Shoemaker-Levy. And as it passed Jupiter, it broke up into small, roughly 2 kilometer in diameter chunks. That's really only like about 1.5 miles chunks, okay? So they were, broke up. And then what they did is they kind of orbited around our solar system, and they came back in 1994, and they impacted Jupiter. And this is the first time that we had ever seen an impact occur. And that impact actually broke, if you look over here on the far right, this is the result after the impact. All of these holes that you see punched in the atmosphere of Jupiter are all Earth size or big or larger. So if that comet had hit the Earth again, and then there were about 20 of these fragments, it just would have destroyed the Earth. We would have been completely destroyed the Earth. Fortunately, we had Jupiter there to break things up and to take the blunt for the Earth. And I should let you know that Jupiter is about 1,000 times larger than the Earth, and it has a much more dense atmosphere than our Earth. So it was able to take care and absorb the blow of this comet. But we have had what we believe to have cometary impacts in Earth's past, and it wasn't a very good day. So I don't know how many of you have ever heard of Carolina Bays, but this was an actual geological formation that was discovered in the early 1900s by a North Carolinian, someone who was working, I think, from UNC, and they were studying these odd formations in North Carolina. They're called Carolina Bays. And what's really odd about them is that the majority of them, first of all, have no tributaries, yet they have water in them. They're all semicircular or more ellipsoid actually in shape, and they're all deeper at the southeast end and shallow at the northwest end. And they're all kind of all of them are always located in a northwest southeast pattern. And so you can see up here that I've got some in the middle panel up here, some things from Canada, basically. And so what's from studies, they believe that this was actually a comet that impacted the Earth in the Ice Age. So probably somewhere between, I have 10,000 BC, which I think is where it actually was the impact. As you read other websites, you're going to see differing opinions on dates. I think that the jury is still out on the exact dates. But we do know that right about this time, we had the disappearance of the woolly mammoth occurred, and we also had the disappearance of the Clovis people, which were an indigenous people that lived in the northeastern and southeastern United States. They were prevalent in North Carolina, South Carolina, and on up into Canada. And so something actually cause an extinctive event to occur. The idea is that most likely we had an impactor up in Upper Canada that hit, or maybe possibly in the Minnesota area. There may have been more than one that actually hit the Earth and broke through the ice. Now you got to remember that during the Ice Age, we had super massive sheets of ice that were over the United States. And so I mean, we're talking about mountain moving size chunks of ice that, you know, carved valleys and rivers and actually deposited large ledges on tops of mountains. And so that's the kind of ice we had. Supposedly this impactor must have hit in Canada, and then the ejecta, which we call the stuff that kind of flew out after it hit, is what formed these bays. We have these large chunks of ice falling into North Carolina, and now they found them in other places around the United States that that just rained down and carving these bays out. And then what they do, well, as the temperature warmed, they melted, creating these lakes that we call Carolina Bays. But we do have a mass extinction event occurring right around that time, right about the formation of the bays. We have the disappearance of woolly mammoth and the Clovis people. So it's very possible that we had, you know, which also, you know, precipitated, kept the ice age going longer. So it's very possible that this is what happened.
Mm-hmm.
All right.
And
Any questions?
yeah, can you see this question? Elena wants to know, can we tell what a comet is made of just by what it looks like the color or the length of the tail?
Yeah, that's a really great question, Elena. And yes, mainly from the color. So we look at the spectra. So as the sun is hitting the comet, if you recall back a few slides ago when we had that green coma and everything, based on the spectra, the color of green that it's emitting, we know what kind of chemicals, what the predominant chemicals are. A few years ago, we sent a probe out around a comet. It was actually had an impactor on it. It was actually called Deep Impact. We impacted a comet, and then we sent down an impactor. So it's just like a copper disc that went in and hit a comet. And then our probe went around the comet and it looked at the spectra coming up. And it was mainly formed out of mainly silicas like clays and such like that. But then we detected other kinds of elements in there. But when a comet comes around, we can do spectral analysis, and every element on Earth and every compound emits a color when it's burned. And so we have over time, we've developed a table of what these elements look like. And through spectral analysis, we can actually tell what kinds of things are. But there are some really, you think about a comet like the size of the one I showed you that was hit with that was set up by LA. I'll go back to the prior slide, hitting the Earth, and it's comprised mainly of cyanide. What do you think that might? I mean, it really could do damage to our lakes and streams and anyone drinking out of them. So there is a real danger here. And let me see here. We'll talk about asteroids in a second. But yeah, it could happen. So we've known about this since 1994. We've known that there are objects floating around our solar system that need to be deflected in case they come to Earth. And we've known about this since the mid 90s. Yet we've talked about it. We still don't have one deployable technology that would deflect a comet or an asteroid from hitting the Earth. Right.
That's kind of scary to think about.
It is kind of scary to think about, especially because we know that we should be doing something about it, and we're not. So, but I will say that we're overdue for such an impact, and it could happen. So just let you know that is a possibility. All right, let's go to the next one, and that's about we'll talk about near Earth asteroids. Now, this is something that we really didn't know a lot about. We knew that there were a few asteroids out there that were circulating in the outer and inner solar system. We knew about the asteroid belt way back in the 50s and so forth. But in the 90s, we began kind of mapping asteroids, and you can see this is a map of what it might have looked like in the 1990s, and then later in the 2000s, you see it's getting actually a lot more. This was in 2018, and then we get in, and all the known asteroids that we had. And this is really only a couple of years ago. And I know now that when we talk about Earth, there's over 2,000 near Earth asteroids. And oops, let me go back to that here. pull this off here.
I always think this is like just a crazy fact. Like when you see it in this kind of, you know, diagram, it really puts it into perspective.
It does, doesn't it? I mean, there are a lot of asteroids that are floating around us. Now, the thing is that's great is that when we say that Earth has cleared out its orbital path, what that means is that Earth is never where another asteroid is, ever. So occasionally something, we do run into something, but we're pretty much cleared. But it's just that if we have this really interesting game of dance where we're never where our partner is, where we should be. And so the Earth is pretty well protected, but there are now a lot of asteroids. Again, this is another one where we actually have the technology to actually encounter and deflect these asteroids. We just haven't deployed it. And so there's nothing deployable or tested yet. We've got a lot of great theories, but we are sitting in, again, this outer brown band is more the asteroid belt. This yellow orbit here is Jupiter. This orange one right here is Mars. The blue one is Earth that I'm circling right there. But they're just, we just haven't done anything about getting, really cleaning this mess out. And we know that it's actually beneficial. We've done the spectral analysis on a lot of these asteroids, and we see really interesting things like precious and rare metals in these. Some of them are actually made of gold. And so we're not going out there and getting any of them. But they do represent a good opportunity for Earth in the sense that there's a great opportunity for mining these asteroids. There's a lot of natural materials. We don't have to rip our own Earth up trying to mine materials or worry about the environmental impact. We can just go out and mine an asteroid in space where things are already pretty dirty to begin with respect to radiation and pollution. So, we can mine them freely, but if we don't do anything about these asteroids, eventually one is going to hit. And we actually have had a few hit the Earth even recently. So I'm just going to kind of go to this next page here. If you want to track that on a regular basis, there is a site that's pretty cool. It's called spaceweather.com. This is a free site. You just go to www.spaceweather.com, and they're looking at all kinds of really cool things. I'm going to pull one over that I looked up last night off of Space Weather. Just give me a moment here. I'll find it. Well, I can't find it right now, but I'll try to pick it up a little bit later. But what's really neat is that anything that's happening with respect to aurora or sunspots, things like that are always on this page. But one of the really neat things they have is every month we track asteroids. And so asteroids are coming around the Earth all the time. And usually, like for instance, you'll have this one highlighted in red. This one was 0.009 lunar distances. This one actually hit Earth back in 2012. So it was, it was a pretty climactic event. It was, so that was the one over Russia a number of years ago. If you recall, it actually exploded over Russia. So so every now and then they do strike the Earth. So they do track them. And really, you can take comfort in one thing, is that really the ones, all the really big ones, like you see some here that are 3.4 kilometers, but usually don't hit the Earth. They're usually far enough away that they never hit us. It's the really tiny ones, like this one's like only 35 millimeters, 40 millimeters, 65 meters here. Sorry, not millimeters, but meters. 65 meters only hit the Earth, and if they hit the Earth, they usually explode in the upper atmosphere. So we're in pretty good shape with those.
Right.
All right, let me go on because I'm getting kind of close on time. We do know that a massive asteroid, the idea is it may have been about 7 miles in diameter, hit the Earth 65 million years ago. This is the one off the Yucatan Peninsula that actually is thought to have caused the extinction of the dinosaurs. So they do hit. We do find their craters on Earth. We are due for an impact of a big one. So it's just something that, again, something we need to develop as a technology. Let's talk real quick. I'm going to move on quickly about dual coronal mass ejections. This may not be one you've heard of, but every now and then the sun actually, especially during solar maximum, which we are now headed towards solar maximum, will belch out a lot of material, and that will be headed towards the Earth. The Earth, fortunately, is protected by this beautiful magnetic field. That's what I have out here on the right. And that, for the most part, it does protect the Earth, and it keeps all this radioactive material from hitting the Earth. Instead, what the magnetic field does, it shunts it down to the poles, and we usually get that beautiful aurora borealis. That's what causes aurora borealis. And so we're relatively safe. Occasionally, though, one does get past the magnetic field, or is so powerful it causes the magnetic field to collapse. This is an example of magnetic field collapse. This actually happened 13th of March, 1989. And there have been others since then, but they are rare. So let me just say that it does happen rarely, but it does happen. And when that happens, then it affects our power grid. This one actually caused a massive blackout over the United States. This is a map of the United States. It might be a little dim, but this kind of shows the areas that were affected. And then literally the Northeast actually collapsed in terms of the power grid. And this is nowadays for us, this is a thing that's really the major issue is that it could cause collapse of the power grid. And this was, of course, this only lasted a few days, but in 1859, there was an event called the Carrington event. And when we have we've discovered one of the things in the last 50 years is that space is not vacuous totally. There's a lot of stuff a lot of goop actually sitting between us and the sun called interstellar medium. And so when the sun sends out a coronal mass ejection, that goop kind of slows it down and keeps it from hitting the Earth, and that gives Earth time to move out of the way. But in 1859, there was an impact that was noticed by this astronomer named Carrington. And what happened was it was a dual coronal mass ejection. We had a first coronal mass ejection it took a few days to hit the Earth, but what it did was it cleared out all that interstellar medium between the Earth and the sun. And right behind it was another coronal mass ejection. These ejections happened twice, one behind the other. Well, anyway, when the second one hit, it actually completely collapsed the Earth's magnetic field. And you could see aurora borealis all the way down to Cuba, so which was very unusual. But what we did at that time is this was during the days of telegraph. And so all those telegraph wires strung across the United States acted like big antennas. They absorbed all that energy, and the energy traveled down the wires to the telegraph stations, and they all burst into flames. So it was a pretty tragic event for telegraph operators when that occurred. For us today, it could do the same thing, travel down our high tension wires, hit the high tension electrical transformers. And the NASA's computed this. They believe that if they exploded enough high tension transformers, we could be out of electricity for 12 years. Because it takes time to build those transformers, and we don't have about 12 or so in stock at any one time. So the real possibility is that we would have no electrical grid, functioning electrical grid for about roughly 12 years if something was done. So I will say that to fix this, NASA has been working with electrical companies in the first world, but second and third world countries have largely ignored the warnings and aren't doing anything. So for first world countries, I think that we do monitor the sun regularly, and we do send out alerts to power companies when something like this is going to happen. It gives them a chance to take things offline and to shield their transformers. But it's hard to say what would happen in second and third world countries if something like this were to happen.
And Linda asks, how much radiation were people exposed to during that event?
Yeah, it's hard to say how much radiation they received. Hard to say how much cancer developed. We just weren't really tracking those kind of stats, and we weren't even equating that. We didn't really understand the sun in those days that they're sending out a lot of radiation. So that's a great question. It's unfortunately one that I think that further study would have to be, incidences of cancer in the United States. You also got to remember at that time, people really weren't keeping good medical records. Believe it or not, with the generation starting after World War II, the baby boomers, we're really the first generation that comprehensive medical records have been kept on in the history of the world. So this is something that knew this happened. We're beginning to correlate a lot of these pathogens, carcinogens, radiation exposures to direct incidences of cancer and stuff, something we haven't been able to do in the history of the world. So that's a really good question. Unfortunately, it's not one that we really know. They didn't even really understand radiation at that point. You got to remember, Madame Curie didn't come along with her discovery of radium until the late 1800s. So these are just things that we just didn't know about at that time.
Yeah. So hopefully we won't find out how much radiation we
exactly.
get exposed to. Yeah.
Exactly. All right, let's go on to the next one because we are running a bit short on time. And Laura, if you just keep me honest there in terms of time and everything, that'd be great.
Oh, sure. Yeah.
One of the things that we do, this is something we can do something about, and it's UVA, UVB radiation. Just real quick, UVA, UVB radiation is actually generated in the chromosphere of the sun. There is another radiation, UVC, but that UVC is mostly absorbed by our atmosphere, so we don't really have to worry about that. But UVA and UVB do come down to Earth, and if you're looking at the sun, also too, there's a lot of energy there. You can damage your eye, and you can damage your eyes, permanently. This is a case of, and I have here on this slide here, solar retinopathy. And so this is the case on the right here where someone was looking at the sun for an extended period of time, and they literally, their retina, which is this discolored area right here in the middle on the right panel, was actually got a sunburn on their retina. Now, they can clear up, but it does take a long time. And if you stare at the sun long enough, you can permanently damage your retina, and you'll have impaired vision after that, impaired or no vision. So I do caution you to, first of all, and let me just say this, that sunglasses that say 99.99% blockage, that's only a claim. There's nothing verifiable by that. Please do not put sunglasses on and then stare at the sun, or even multiple pairs of sunglasses. That just doesn't work. So you can get a lot of radiation, a lot of UVA, UVB radiation going here and just literally cook your retina. And so let me just say, please don't do that. That's something that we can control. All of us can. So please don't do that. Over here on the left is a healthy retina. This is what a healthy retina looks like, healthy eye. So, you don't want to cook your retina because this may not come back, and you might suffer an entire lifetime of blindness or impaired vision. So that's one thing we can do something about. Another thing we can do something about is, of course, sunburn and skin cancer. There's a cancer on the right hand, or on the right. I can tell you that I'm a personal survivor of skin cancer. I actually lost 66% of my right ear a few years ago. It was rebuilt with plastic surgery. But because of exposure, I grew up in Florida and running around with copper tone, and that was, I of course suffered from a skin cancer. You just don't want to get burned like this. You always want to use sunblock when you go out in the sky in the day. These are two guys right here on the left that didn't do that, and they look pretty cooked. So please use skincare products, sun blocker. This is something you can control. Now, you can't control whether a comet hits our Earth or an asteroid or one of those other things, but you can control this. So please use sunblock because it will adversely affect you. Even if you get burned and you don't see any effect, later when you get into your late 40s and 50s, your skin, because of that initial dose that you may have received as a teenager, will actually begin to develop a cancer because of that. So just don't think because you're young and you're viral, that you're not going to experience something like this. You can. Mm-hmm. All right, next one. I'm going to just talk about super flares. You can see this is the Earth with respect to a super flare that occurred in 2003. Now, we weren't here. This is just superimposed by NASA. Okay, so we were in no danger. But super flares are a little like if you have a lamp on in your living room and you run into your living room, or run from your living room holding the lamp, and it pulls out of the cord out of the wall, the lamp goes out. And that's a lot with super flares. We really have no fear from super flares. They do lash out during solar times of solar maximum. These are some example of solar lines of flux on the sun, and then when they snap, they're kind of like a rubber band throwing usually, of course, this big plume of plasma and fire out from the sun. But then as soon as they leave the sun, they dissipate. So there's really nothing to fear of these things. Again, usually accompanied by a coronal mass ejection. And it's the coronal mass ejection we have to worry about. And again, some of them can have quite a bit of energy. Some of them sometimes 10 million times more than a volcano erupting. So they're really quite hot. Again, as soon as one leaves the sun, though, it usually loses all of its energy, so you don't have anything to worry about super flares incinerating the Earth or something like that. We do have to worry about the coronal mass ejections that usually accompanies a solar flare. So we already talked about that one. Mm-hmm. We have the red giant phase of the sun. There will be a point in time where the sun actually loses its ability to attract itself to itself, and then it'll expand to be the size of a red giant, which will be about the size of our orbit. And at that point, it may incinerate the Earth, but that's going to be about 5 billion years from now. We don't really have anything to worry about that. Here's some examples of some stars that have gone into the red giant phase and then actually after that turned into novas. They're really quite beautiful in the night sky, but this is literally the death of a star here that we see.
Wow.
Earth's magnetic field is one that's weakening right now. I'll go to the next slide. It actually shows, we can actually see, this is actually from 2000. We've been monitoring the field. It's been moving ever since we started looking at it in the 1600s. And now in 2020, it's just a bit south of the North Pole. So it is changing. But let me just say this again, even though it's weakening, and if we look back in geologic history, there are no extinctive events associated with the flip of magnetic field or with a weakening field. So we're pretty safe from that. Global warming. I do want to touch on this really quick. If you guys were familiar with the fires that occurred over the summer, this is something that really is happening. It's something that we can do something about as a world. If you look here, you show the fires from California. This is on the upper left hand. This is the derecho that occurred over Iowa in June of this past year, and it wiped out 1/3 of the corn crop in less than 3 hours. So that was really powerful. Wow. We also had a really active hurricane season. This was a Hurricane Delta. We were already in the Greek letters, so we had a lot of hurricanes. This one actually went from a Category 2 to a Category 4, actually hitting Louisiana later on. So that was really powerful. This one down here is on the left hand. You may not realize this is a nice canalway, right? Looks like a nice river, right? This is actually I-40 back in 2017 when Hurricane Florence hit. And it actually was a weak hurricane. It was only like a Category 1 by the time it got to North Carolina and stalled over North Carolina. But it was very, very powerful. Dumped a lot of water completely. This is I-40. This is our I-40, not far out of the triangle. So this is how it looked. And I happen to know because my daughter was getting married at that time, and I was actually having to dig a trench in my yard to drain water off so our wedding guests could come to our house. So it was a really powerful hurricane. And then here we have the ice shelf in Antarctica and also in the north, we of course off of Greenland and everything. The glaciers are disappearing at an alarming rate and breaking off, floating into the sea, causing sea level rise. Just to get real quick, this is a study that was done back in the 1980s, and they went back to the 1960s, charted climate change through the 60s up through the 80s. This is where they were in the 1980s. And then they predicted what would happen into the 2000s, all the way up to 2000. This is the end of 2019, and the top of the graph is 2019. This was a predictor, okay? They didn't really know what was going to happen. But this on the right is the actual. And if you looked at the predictive model and the actual model, we hit the prediction model. So we didn't change our carbon. We basically took as carbon was continually emitted in the atmosphere, that went up. Now the green line below is what we call solar irradiance. And I didn't really go into the prior panel, but our exposure to the sun was predicted to actually drop, our warming with that would only be about 4 degrees C. We would have hit that 4 degrees C, but because of the carbon that we emitted, we actually hit, and we actually met the prediction that NASA predicted way back in 1980, and we hit that this year. We were exactly on target. That means that mankind is contributing to global warming. So guys, the importance is to us. This is not a political thing. This is what's really happening. So we are really ramping up our carbon emission into the atmosphere, which is warming our atmosphere, and it's causing all these super intense storms and fires. Now, if you look right now, there's an intense storm happening over California. There's literally a river of water, of moisture flowing into California, and they got fires in the summer, and now they're being drowned in mud and rain and snow. The snowpack in the Sierra Nevadas is, in tens of feet right now. So the intensity of storms is literally doing exactly what the experts said it would do back in the 1970s or 1960s. So it really is happening.
Wow.
All right. So this is and then the final thing I want to bring up, we have 1 minute, is space junk. We just really have to clean up our mess. We've got all sorts of junk floating around in our outer atmosphere. It does fall to Earth. It can hit people. So it is really happening, and we need to clean that up. So that's pretty much the talk. There are things that we can take care of. We can take care of our junk. We can take care of the stuff that we're spewing in the atmosphere. And we can go out, we can take care of, making sure that we have sunblock on and UVA to block UVA radiation. And we can develop technologies to develop asteroids and comets. The rest of the stuff we really can't do a lot about, but we can do things to protect ourselves. And the message is, look, let's do that. Let's start protecting ourselves, because we do have the technology. It's time for us to kind of grow up and do that.
Mm-hmm.
All right. Thank you very much. If you have any questions.
Thank you so much, Doug. I'm sorry that we don't have time to answer all of the questions, but you've given us so much to think about. And I've definitely learned some new things. So real quick, I just wanted to say, again, thank you to our expert, Doug Lively. And of course, thank you to you all for watching. We put a link in the chat to a survey that you can fill out about all of the Astronomy Days programs if you joined us. And thank you to the NC Space Grant for sponsoring Astronomy Days. Thank you to our Friends of the Museum members who support us every day. If you would like a hoodie or a t-shirt to commemorate Astronomy Days, you can get one on our website. Friends members save 10%. And of course, check out all of the other programs that we have going on all week. Through Sunday, at least. And we've got recordings of previous programs on our website available now. So yeah, Doug, everyone is saying thank you. I think you can see the chat now.
Thank you all.
Yeah. Thank you so much for joining us. Yeah. I'm glad we got to number 1. I couldn't cut you off before that. I was like, I got to know what number 1 is.
Exactly.
Okay. All right. Bye, everyone. Have a great day. Stay safe out there.
Thanks.